take all of that information and move from logic to proof. Well, essentially what we've been doing is we've been proving things. We're starting with some premise and we're moving things forward. What's important is that this conclusion was invalid. He is a computer science student, but this is not a valid conclusion. And so the argument is invalid. The conclusion might be true. So you can see that the conclusion has a truth value, and that doesn't matter when it comes to the validity of the argument, whether or not the conclusion is true. If the argument is valid, the conclusion will be true. But it is possible that the conclusion is true despite the fact that the argument is incorrect. Okay? And so I'll ask about two things at a time. Yeah, how would you possibly conclude, make that conclusion? It's just luck that you got it right at the end if you're not following proper logic. Okay, so there's some terminology when it comes to proof. So when it comes to proof, there's a few key words, and there are a lot of them actually, but we're only going to deal with a few. The first is a conjecture. And a conjecture is just a statement that we're proposing to be a true statement. So I'm going to take as my premise, I'm proposing that this is true. It's a conjecture. I have a conjecture that all computer science students are the best students at Dalhousie, right? To make that a theorem, which is a statement that I can show to be true, I would have to have something called proof. And so I'd have to start from the premise, my conjecture, and I would have to follow a sequence of statements that demonstrate that it is a fact. And once I can prove that that's the case, then it's a theorem. It's a statement that can be shown to be true. It's a conjecture until I have proof, and then it becomes a theorem. Okay, so theorems. Know them when you see them. There are a lot of theorems that you have held as fact throughout your life, and behind them, behind the scenes, there was a logician or a mathematician or a computer scientist that was proving that these were true. And so now we state them as fact because they are facts. Once they've been proven, they become a theorem, and now they're true. Okay, so for instance, we see if x is greater than y, where x and y are positive integers, then x squared greater than y squared. Okay, well, that doesn't look like my universal quantified statement, right? There's a lot going on there. How do I translate that back to what I want to see so that I know which rules of inference I can apply? I can do that because the universal quantifier is in there. So tell me what my universe is. And I said it's a universal quantifier. I should have just said it was a quantifier. Yeah, the universal quantifier is saying for all x and y for all x and y in the positive integers, so in z greater than 0. Okay? And so we can rewrite that whole statement to look more like what we want to see. So for all, it's not that far off, but for all positive integers, x and y, if x is greater than y, then x squared is greater than y squared. So how do we then start? Because we'll have plenty of time to cover proof, but how would you start when you have this idea? You've got all positive integers x and y. If x is greater than y, then x squared is greater than y. What is my starting point? Well, it depends on the type of proof. And we're going to see different examples. But this is first steps for something called direct proof. And that's the first, probably the most simple way forward. And that is because this is a path. If you are starting from, if we're starting from some premise and we're trying to go to some conclusion, there are proofs that take us in all directions. But this is the most direct one. This is just straight line path from A to B, okay? And that is essentially if I have, if I'm trying to show that P implies Q, which generally we are. We're starting with some premise. We want to get to some conclusion. I'm going to start by assuming that P is true. So I'm going to start directly from the premise, and I'm going to move directly towards that conclusion as fast as I can. Okay, so the typical starting point is then to say, pick an element in the domain and show this has the property in question. So we're going to pick an element in the domain, we're going to show that it's true, and then we're going to use universal generalization to imply that it holds for everything in the domain. This is called direct proof. It does not go in different direction, it goes straight. Okay? And direct proof, essentially, to boil it down into something that I think is easy to think about, because we've been thinking about the logic, P implies Q. You assume that P is true. You use rules of inference to show that Q must also be true. That's direct proof in a nutshell. It's a straight line proof. So, 37, we're doing good. Great. Okay, so I just have two examples. We're only covering direct proof today, and then we'll move on to different types of proof later, but this is the idea of direct proof. So, and I've stated as a theorem, because this is not my conjecture, this has been shown to be true, okay? So, the theorem is, if n is an odd integer, then n squared is odd. If n is an odd, then n squared is odd. So the question then, what are we proving? Like, what's the goal here? What do we hope to prove? The most important thing that you want to get to is to think about, what do I want to show? First of all, what's my universe? So I'm going to say my universe is all the positive integers, right? And then we want to say, okay, well, we have a few things. P of n is n is odd. So that's our first piece. And then we can let Q of n is n squared is odd. So if we come up with our sort of notation for what we're going to call it, what do we want to prove? Correct. Okay, so we have the right idea. So we want to show that for all n in z greater than 0, P of n implies Q of n. And so the way that we do that is, we said we're going to take a direct approach. We're going to pick a number, let x be an odd positive integer. And so what would it mean to be an odd integer? So what can we have some facts that we can work with, and essentially that means that it's going to be something like 2k plus 1. So we've got this integer, and we've got, we know that if it's odd, then we know that n is 2k plus 1, because it has to be odd, it means there's a remainder of 1 when we divide by 2. So k is also in z greater than or equal to 0 this time. Okay, well then what can we show? We can square it. Well, what is n squared? N squared is the same as 2k plus 1 squared. And I should say, I assume it's odd because if you think about this, n is n mod 2 is equal to 1. All right, So what's 2k plus 1 squared? Well, you can do that math. You can square things, right? So it's 2k squared, so 4k squared plus 2k plus 2k, so it's 4k plus 1. And you can work this out if you want on the side. You can go do the 2k plus 1, 2k plus 1. If it has been a while, right, you're going to multiply the first with both of them and the last. And so it's 2k times 2k plus 1 plus 1 times 2k plus 1. I did it kind of quickly, but the same holds. So 4k squared plus 2k plus 2k plus 1, or 4k squared plus 4k plus 1. If you don't remember doing that, it's a good thing to remember. it's a useful tool. Okay, so in the end, so that means that n squared is equal to 4k squared plus 4k plus 1. How do I show that it's odd? What I need to do is exactly what I did above. I need to show that essentially at this number mod 2 is equal to 1. So I can do that by saying, well, okay, that's the same as saying that's all equal to 2 times 2k squared plus 2k, all plus 1, right? And that means that n squared mod 2 is equal to 1. And that means that n squared is, what I really want you to do is understand that that's a valid way to prove things. And so the most important piece is then that showing that we can show in direct order that something is true.